All righty, welcome back. There he is. The man, the myth, the legend. Right in the middle of my screen. Let's see what we got.
I just wanted you to know that somebody was actually here.
Oh, I'm sorry. My audio was muted there. What, I missed something there? What?
No, I just wanted you to know that somebody was actually here.
Oh, yeah, thank you. Okay, now I didn't know if you could even hear me or not whenever that's mute. I guess the muting just is only for incoming. I can't hear it whenever it's muted, but I guess you could still hear me. So, did you watch the hockey game on Saturday, delayed by 8 hours?
I only watched a little bit because I have some plumbing issues to take care of.
Oh, good Lord. Okay, well, yeah. Oh, good grief. That's a mess, isn't it? I got some of that taken care of today. So I didn't watch all of it. I came back. I just kind of funny of these outdoor hockey games. I guess if the sun comes out, that's kind of bad news, isn't it? So, anyway, so hopefully, yeah, it's just, oh God, I can't even imagine what everybody's going through right now. What a mess that was. I guess that earlier in the week, I was out of power about 34 hours. And then toward the end of the week, water became an issue. It's right out by my irrigation system, but also was affecting the water to the house. My irrigation guy came today and took care of it instead of a plumber. He said he'd never seen PVC pipes look like that before. It looked like I'd hit him with a baseball bat or something, but nope, just frozen and shattered. Okie doke, let's share screen here and get the show rolling here. We got a lot to knock out here today, but I remember knocking out these same sections in one day last semester, so I know it can be done. Seems like a lot, but okay, let's make sure I put it on share screen. Okay, share. And then let's get this going up here. Oh, yeah, somebody, I thought, did I get rid of it? Somebody just said hello with a chat. Okay. Here we are. So we're in 3.4. So, but, you know, got a lot. One of these sections only has like 2 pages. It won't take long to cover, but this one's got a little meat to it here. So now we did numerical descriptive measures for a sample where we had the sample mean. That's the X with a little line above it that we call X bar. Now we're not doing median and mode again, just the mean. Now for various reasons, because they need to have different symbols, even though the calculations are going to be the same. But we have, whenever we're talking about population, the symbol we use for mean is this little Greek letter. Statistics likes to use Greek letters a lot for your population parameters. That's very common. This one, you know, it looks like you can't decide whether it's a U or an M, but actually that's a Greek letter. It's called mu. It's okay if you don't know it's called mu, but as long as you can sort of visually recognize that you know that's the population mean, that's helpful. And it's the same thing as normally calculate the mean. You add up the values and then divide by your, in this case, population size instead of sample size. Now they use capital N for population, where we use lowercase n for sample. That doesn't make much difference, except for, we're not going to cover it in this class, but there are some things where you have both capital N and lower n in the same formula, so you would need a distinction. We're not going to need that distinction though, so it doesn't matter that much. But it's the same idea, add them up, divide by how many of them you have. It's just now mu if it means population. Okay, so I don't think I have to explain how to add those up and divide by 5. So now let's talk about variance. Now we talked about sample variance before. Now this actually is a different numerical value. The mean won't make a difference. It's calculated the exact same way, but this is calculated differently. Slight difference. Now you're going to use technology to do this. I imagine you're not going to have to worry about the formula per se, but but I want you to know why it's a different answer. Because the formula, if we recall, I can bring it back up, I guess, real quick here. Let's see. What section was that? Measures of variation and shape. Let's see. Should be up here somewhere. Yeah. Oh, come on. Well, anyway, okay, here we go. Just as a reminder that the formula for the sample was always divided by n minus 1. This one is just divided by n. Therefore, that's obviously going to make it a slightly different answer. So that's the difference here. But like I said, you're not going to have to worry about most likely doing the actual calculation using the formula. So, and I'll talk about whether we're using Excel or the TI calculator. The TI calculator shows both the standard deviations for sample and population. And just like before, even though this is a brand new formula, I'll say this statement again, because it's always true. Anytime that you have a formula that represents the variance of something, the standard deviation will always be the square root of that particular formula. That's just a automatic rule. Our variance formula is a little bit different here, but the standard deviation is always just the square root of whatever your variance formula is. So that's nice to know. That's consistent. So anyway, and like I said, this little thing right here, I don't think you have to worry about. We could probably skip over that because you're not going to need to do anything probably manually like this. I probably could get rid of some of these notes, I guess. But anyway, I'll show you technology-wise how to do these. Let's look at this little block of 5 numbers. So, I mean, if you want to ask me sometime about the calculation, if you're just curious or something, but I don't want to use any lecture time right now to do it, but I'd be happy to, explain it to you sometime if you wanted to know. But now in the calculator, you'd put the 5 numbers in there. So it doesn't matter what order. 2, 10, 6, 5, 9. All right. Yeah, imagine we're really rusty here after kind of 2 weeks off here. Yeah. Well, we're going to have another gap coming up after spring break too, aren't we? Let's see. 2, 10, 6, 5, 9. That can't be right, can it? Oh, I was right. Should treat myself with a cookie or something. 6, 5, 9. So we're using the same 1-bar stats that we've always used before here. So I'll go second, quit. So nothing's new. This is more of a review of how to use this thing. Calc, 1-bar stats. And if you're just using like a TI-83, it's not going to show all this, but just as long as everything's in L1, just hit enter because it defaults at L1. All right. Oh, forgot to hit enter. Now here are both of your standard deviations. So your SX, that represents your standard deviation, and then your little, oh, I forgot to mention that little symbol, that little O with the hook is called, it's sigma. It's actually lowercase sigma. Once again, this is not a Greek alphabet test here or whatever, but I like to say that. There's a little O with kind of a hook there. Surprisingly, it's this zigzag thing for the summation. In the Greek alphabet, that's actually capital sigma. So that little O thing is lowercase for that, which may seem strange, but, think about the, English alphabet. We have a lot of cases where the lowercase letter doesn't look exactly like the uppercase. Of course, that one looks kind of, extremely different, but anyway. So so it's the same thing I just had in the calculator right there. And we talked about this before, so let me mention this again. If you were using the calculator and So I mentioned that to go from variance to standard deviation, you take the square root. If you wanted to go standard deviation to variance, you would square that number. So you would have to take the 2.87054, whatever. That's probably enough digits right there. Stop at the 4 and hit the square key, not the square root. And that will take you back up to right there, the variance. That would be 8.24. All right, in Excel, we're going to see two commands that are extremely similar to what we saw for the sample. The only difference is when it's population, it'll be .p instead of .s. We had this before in that section, so the sample variance was var.s, so the population variance will be var.p. And then same thing with standard deviation, so it'll be stdev.p instead of s. So that's the difference between population and sample. And then there's the 2.82705, blah, blah, blah. There it is that way. So, okay, so that's not too difficult to come up with. Now let's talk about how I mentioned this before last time, a couple of weeks ago, about the standard deviation is, you don't necessarily get a lot out of it just by the number itself, but how the mean and standard deviation work together. Now let's see, I think we did do, still getting used to this book. What, 3? That was, 3.3. I don't know if we did. Let me look at the 3.2 for a minute. Well, I think we did do, let's see, I don't know, something. All right, well, we did, okay, a couple of things. We're going to do a little more now. Okay, we did the coefficient of variation, then we did the z-score. That's what I thought of, using the mean and standard deviation together, working them together. Now we're going to explore that a little deeper here, some other ideas here. So, of how they team up together to give you information about a data set. Now we're going to have a rule called the empirical rule. All right. All right, now, those are talking about right skewed, left skewed, where they cluster, blah, blah, blah. Anyway, what we're interested in now for this is, for this rule to apply, it only applies, it should say bell-shaped and symmetric. I'd rather it say symmetrical is kind of, should say bell-shaped and symmetric, or just bell-shaped is good enough. They need to indicate, and I make it real clear, I don't make it too tricky here or whatever, but for this rule to apply, it kind of needs to have a sort of a bell-shaped symmetry to it. Let's see if I can go back to those skewing things and show you. We're going to have a different rule whenever that's not the case. Was that? Oh, the shapes were in, we did that in 3.3, I believe. No, that was in this section. Why'd I miss it? Let me go back down. The left skewed, the right skewed. It's right at the very end, I think. Yeah, there we go. That's bell-shaped and symmetric right there. And actually, we're going to look at it as a without histograms. We're going to look at it like this, like here, kind of what we're talking about, that shape right there, where it's symmetric and your values are kind of heavily clustered, the mean and everything's right in the middle. And okay, for this rule to work, the data set needs to be shaped somewhat like that. Now, you're not going to be worried about constructing the shape or anything like that. That's not your responsibility, but that just needs to be part of the definition for this rule to apply. Oh, okay, let me just kind of read the rules out, and then we're going to put them in action here or whatever. So that's okay if the reading of the rules doesn't make any sense to you, but I'm going to clarify it as we go down right in here. So we've got these three values for the empirical rule. And also normal distribution. That's going to be a big part. We're going to be talking the second unit, of course, and on is going to be using. I don't know if we use normal distribution that much right now. It's kind of jumping a little bit ahead of us there technically. Usually we just say bell-shaped and symmetric But yes, that is what's called a normal distribution, which we're going to learn all about that later. That curve I showed you on that blank page, yeah, that's going to be a big part of your life in this class coming up here soon. So in Unit 2. So anyway, excuse me. About 68% of the values should lie within one plus or minus 1 standard deviation from the mean. Okay. 95% of the values are within plus and minus 2 standard deviations from the mean. And then 99.7 of the values are within plus and minus 3 standard deviations from the mean. So let me just kind of explain the first one, then we're going to use all of them in action here in a minute, but I'll just talk about the first one. Well, I might talk about all of them real quick here, but so what this says is, all right, suppose you have a data set that they told you, meets that criteria about bell-shaped and symmetric or normal distribution, and you have a mean and you have a standard deviation. So if you take the mean and you subtract one value, whatever the standard deviation is, you subtract it once to that mean, and then you add it to the mean. That creates an interval, a low end to a high end. I'll use something easy like I'll use 100 and we'll say the standard for the mean and the standard deviation is 20. So if I subtract 20, I'm going to get 80. If I add 20, I'm going to get 120. So now I have an interval between 80 and 120. So what this rule is saying is if you went through your data set and you counted every value that fit between 80 and 120, you counted how many numbers were in that interval, and you divided by the total number of values you have in your data set, you're expecting that percentage to be about 68%. Doesn't mean it's going to be exactly that, but you're expecting that close to that. Now, the larger number of values you have, the more likely it's going to, be accurate, closer to 68%. I mean, with 10 numbers or something, you can never hit 68%. They'd all be multiples of 10. But that's what the idea is. It means you're using the mean standard deviation to create an interval, and that's telling you what percentage of the values then would fit in that interval. So let's come down here and look at some examples of this so we can get a better feel for it. All right, here's, remember this word outlier has popped up a couple times, outlier. Anything that's, if you're not in this last interval, 99.7%, and I think we've actually defined this before also, anything that's outside plus and minus 3 standard deviations, we can call that an outlier. So I think that was we've already said that before, I believe. So, okay, so now I'm telling you that normal and bell-shaped. Okay, I didn't need to draw that picture. I forgot I had this picture right here, but there we go. So that's what this is. This data set would represent a graph that looks something like that. So now I'm just showing, okay, here's one where it's 60 and 8. So we have a mean of 60, standard deviation of 8. And then if I subtracted 8 one time and added 8 one time, I would get 52 to 68. And then if I went through and counted all the numbers and divided by the total that fit in that interval and divided by the total, we would expect about 68% to fit in that interval, 68%. All right, now let's expand this. Let's subtract 2 standard deviations. So 60 minus 2 times 8 would be 44. 60 plus 2 times 8 would be 76. Well, you can see now that we have a wider interval, don't we? Well, obviously we have a wider interval, more numbers are going to fit in that interval, okay? And that plays out right here with that percentage. So now you would, if you went through and counted up how many numbers are in that interval and you divided by the total, you're expecting to be at about 95%. Okay. And then the last case is 3 standard deviations. If you take 60 minus 3 times 8, you'll get 36. 60 plus 3 times 8, you'll get 84. So you're expecting about 99.7% of the data, virtually all, and obviously a lot of times, 100% of the data being in there would not be uncommon by any means. But so you would expect just about all your data to be in that interval. We're going to look into this a little bit further, but here's kind of a couple of examples of type questions that could be on exam 1. Let's see. So let's say you got a mean of 2,400, standard deviation of 450. between what two values do about 95% of the data lie? You know, what between what and what? And here you go. It's telling you assume the bell shape data is bell shaped, and I just put normal distribution there in parentheses. Okay, so I go back to this empirical rule, and I need to know what value corresponds with 95%, the number of standard deviations. So here's the 95%, and the magic number here is plus and minus 2. So that's where I'm getting the 2 from down here, right there. I don't expect you to know these off the top of your head, you know, obviously. You'll get used to them, obviously, just working with them and stuff. So that's where the 2 comes from. That's usually the first question people will ask me, so I always try to address that first, is why I picked 2. I picked 2 because of 95%. If that would have been 68%, that would have been a 1. And if that would have been 99.7%, that would have been a 3. It either would have been 1, 2, or 3. Now, when we get to the normal distribution material, we're going to expand our knowledge beyond 1, 2, and 3. You know, it might be 1.23 below and 2.15 above, so it'll be a little bit different then. But for now, it's just 1, 2, 3. That's it. Okay, the calculation's easy enough here. 2400 minus 2 times 450 is 1500. And then 24 plus 2 times 450 is 3300. So there's your interval. Now, so a question on test could be asked this way, or it could be asked the next way, where I'm giving you either way you're given the mean and standard deviation, but I'm either giving you the percentage and asking for the interval, or I would give you the interval and then have you come up with the percentage. So one way, but you know, as long as you have the mean and standard deviation, you can do it either way. It's no trouble. That's the key. So this one we're going to work it the other way. So we have a data set with mean 80, standard deviation 12. What percent of the data would you expect to be between 44 and 116? Now I wrote these little equations. You don't have to actually do this algebraically. I'll show you how I did it here in the calculator. You want it, that's just algebraically how it would set up, meaning you just solve one of those or the other, because it's going to be the same distance to either end, same amount. So it's one or the other. And if you solve that, you would get 3 for the value that would fit in here to get the low end and the high end. Same number. And 3 goes back up. I won't scroll back up there, but goes back to the rule for 1, 2, 3. 3 means 99.7%. So that 99.7 comes from this 3 right here. But look what I did here. I did this by subtracting, and or I could do it by adding. Anyway, so what I did, knowing it was going to be 1, 2, or 3, I chose subtraction. So I figured out how many times do I have to subtract 12 to get to the number I'm looking for, which is 44. So I went 80 minus 12. Yeah, it's going to either be 1, 2, or 3. 68? No, that wasn't it. I subtracted another 12, got 56. Subtracted another 12, 44. So you see, it took me 3 times of subtracting 12 to get your 44. So that made it 3. So that, you know, without having set up an equation, you can just do it that way. And same thing. If you add 12 3 times in a row, you will get to that upper number of 116. All right. I don't think it's not too bad, I hope. There's another one. This one I didn't show the work in the calculator, but this one, same kind of problem as the one above it. Mean 60, standard deviation 13. Yeah, this was almost easy enough. You could probably do it without a calculator, but I mean, you know, go ahead and use it if you need to. Yeah, let's just say I added this time. You see, if I took 60 and added 13 one time, I reached 73. So it only took one time to do it. So the value K here would be 1, and then 1 by definition on that other page translates to 68%. Now I'm going to show you this little fun thing here. I could do a new example, but I don't know if I want to for time purposes or not. But I mean, if anything, maybe, I don't know if I can do that, but I could throw this and I still need to come up with an Excel assignment for you there. But well, anyway, long story short, this would not be asked on an exam is all I'm saying. I could maybe ask it in an assignment that you had plenty of time to work on. That's different, but no way would this part I'm about to show you here would be on a test. Now, what I did is I use this random number generator in Excel. Let me zoom in on this a little bit. And you tell us it's the normal distribution, one variable. Now, I generated 200 numbers. And I put in, I'm using the same 60 and 8 that I used before. I could have used whatever. I don't know why. And then you have to put in some sort of random 4-digit number. I just put in that number, any 4-digit number. That's sort of, I'm no expert on random number generators or whatever, but it'll be a different data, block of numbers depending on what you put in there. I could have just put A1 and have to put I don't know why I put that Z. Now, A1 would have been fine because it's just going to dump it straight down a column anyway. It's under that data analysis tool. So I generated 200 random numbers it's supposedly creating. However, you always I kind of always wonder how random is a random number generator, but that's, I'm not trying to get philosophical here or whatever. We don't have to worry about that. But Excel would have spit these out down one column. So what I did, I took them, sorted them, and organized them just so I didn't have 200 numbers going straight down a page here, obviously for note purposes here. So I sorted them and then cut them in blocks of 20 so we can see them easily. So all I'm doing here is I'm just trying to test out the empirical rule for this particular set of data. That's all I'm doing, just to see how close, how accurate it is for this set. So you see that there are the three intervals, 52, 68, 44 to 76, 36 to 84. And then over here to the right in blue, those are the empirical rule percentages we're expecting it to be close to, either right at or close to. So then I went through and counted. Now, when I said, just to mention, I'm not going to go through the count here, but of course it does make this easy to count because they are in columns of 20, so when you're counting columns, it makes it easy. But when I say 52 to 68, I don't round here. I literally mean the first number that's either 52 or higher. So I would have counted right here. Oh, hang a second. Got my stylus here. I could just draw that when I'm trying to use my mouse. So in other words, I'm not using that 51.98. It's not rounding. I want literally to cross above that 52. And then on the upper end, I don't go beyond 68. So I go to the highest number before it crosses to 60. Okay, right there, 67.98. See, the next one goes over 68. So those, including those two numbers, and then everything between, count those up, and it ends up being there's 136 numbers. And there's 200 total. So that's 136 divided by 200 is 68%. So that would actually hit the empirical rule right on the number there or whatever. Now the next one is 44 to 76. So I would start, I'll use a different color here. The first 40 be right there, and 76 be right, right there be the highest one. Now this one, it's easier to count what's not in your interval than what is. You see there's only 3 numbers here that are above, 2 below. So it's easier, to say that we've got 5 numbers that aren't in there. So that means there's 195 that are. So we get 195 divided by 200. Okay, so we get 97.5. That's not exactly 95%, but it's certainly not unreasonable. See, that doesn't mean it has to hit that percentage, but we're expecting it to be close to that. And then, as I said before, if I did this with 2,000 numbers, I would expect it to be even more accurate. The more numbers you have, the more likely it's going to hit those. And then 36 and 84, then this is not uncommon for this to happen. They all fit in there. So 100%, but 100% is pretty darn close to 99.7%. Sometimes class I'll do an example of one generating one, but I'm kind of worried about for time purposes here if it's really worth doing or not, since you're not going to have to do it. I could look in the last semester notes, and maybe if I did it, I might just paste it at the end of these notes and make an announcement. But I don't know how sad you would be if I didn't do it. Would you be sad or not sad, or they don't care too much? It's okay if you don't care. I won't be offended. I was just going to do one with 1,000 numbers just to see how close it was. See, it's yeah, I'm not really looking at you, so I can't tell if you're sad or disappointed or not, That's all right. So I'll go ahead and move on then. Now, here's a theorem that we use whenever it's not bell-shaped and symmetric. So it doesn't, like for example, it just is, as long as the data set, the problem can either just flat out tell you to use this rule, or it could say something like, suppose you have a data set that's skewed right, or unknown, unknown, skewed right, skewed left. Anything other than bell-shaped or normal distribution, anything else goes with this rule. Now, this rule is not, you can't really rely on its accuracy that much because, because we don't know the shape, or even, so it's just really kind of a rough guess per se. It's not as good as the empirical rule, but the empirical rule only applies to one situation. So this is just sort of a general rule to cover a bunch of other stuff. So it's just, but it's just something to kind of cover. All right, let's see. Now, for this one, it's very important, very important. That's why I got this in red. That if you have a problem like this on the exam, that the wording for this one must say at least. Now the empirical rule said approximately. That's fine, or it could say about. Or for the empirical rule, it just needs to be wording that it's implying just that one number only, like approximately this or about this. But this one is sort of creating it like an interval. That's why it's really, really kind of a rough guess here. And I only use 2 of them for these. Now this one, the K, once again, the K means the number of standard deviations. And here's the formula that generates it. K, you can't even use 1 for this one because 1 wouldn't work. It would give you 0. So the number's got to be greater than 1, but it could be anything greater than 1. It could even be like 1.5 or something like that. It doesn't have to be a whole number. We'll see what happens in the homework regarding that. On a test, it's not going to be that way. Test, it would be, I only use usually 2 or 3. Maybe I could, maybe 4. I didn't put 4 in there, but you can calculate 4 pretty easily. I'll show you. I'll do that in the calculator here in a second. I'll show you. But the wording needs to say at least. So for 2, it would be for Chebyshev at least 75%. And then for 3, it would be at least 88.9%. So you don't want to confuse this 2 and 3 with the empirical rule 2 and 3. Remember, the empirical rule for 2 was 95%, and the empirical rule for 3 was 99.7. So let's say if it was 4, let me show you how to do 4 in a calculator here. So we would go 1 minus 1 divided by 4 squared. And then, well, I could just hit enter, but I'll just go ahead and put times 100. That just makes it a percentage, but I could have made it a percentage without doing that, obviously, but okay, there it is. So if it was 4 standard deviations, the rule is it'd be at least 93.75%. So that comes up, that won't be on test, but if that comes up, it gives you some other number like that. Just calculate the appropriate percentage doing it this way. So that's not too bad. Okie doke. So women's track athletes, so we have a mean of 57.07, standard deviation of 1.05, shape of the data is unknown, find an interval that contains at least 75% of the data. Okay, at least 75%. So we need to know what is our magic number K here. And then, so at least 75% right here, 2 standard deviations. There it is written in words. And then here it is over here, K equals 2. So that's how I know what number goes right here. So I take the mean minus 2 times the standard deviation to get 54.97. I take the mean plus 2 times the standard deviation to get 59.17. So we would phrase our answer as, once again, that's what that read, at least. You know, if you see something on test that says at most or something, don't ever pick that. It always has to say at least for Chevy Chef. The data lie between that interval, those two numbers right there. So, okay. Oh, here, okay. The data unknown, that's how I knew it was Chevy Chef. Problem may tell you Chevy Chef, which obviously makes it even easier, but it was not telling you it was bell-shaped or normal distribution. So same thing here. So you see this one tells you the data is skewed right. That automatically implies Chevy Chef rule. So you can still use that calculator trick here. It's just the answer is going to be different. So you see it's given us the interval. We have the mean and with standard deviation. This time I just chose to add instead of subtract. I can go either direction to reach whichever number I'm trying to go to. So you see I took 60. I added 3.2 3 times to get to my upper value of 69.6. Or I wrote it out algebraically, which you don't have to solve the equation. But that equation would be solved for 3. So either way you can get 3. I think the calculator way is just fine. It's fine doing that real quick and not having to write all that out. So it took me 3 times. So that's my 3. But then we have to know what the answer is for 3 on the Chevy Chef rule. At least 88.9% of the data would lie in that interval 50.4 and 69.6. So I think as long as you remember to use the at least, and then don't confuse the answer with what the empirical rule answer would be, you know, as far as, so if this last problem had been empirical rule, we would have said about 99.7% of the data would have been in that interval. So it just would have been, you know, this process all right here would have been exactly the same if it would have been empirical rule. It's just the answer would have been different. All right, pretty exciting. Let's jump over here and take a look at a homework problem here. And let's hope it didn't time me out here for being away from it too long. All right, come on. Oh, I forgot to pick our course, but that's okay. I logged in, but I forgot to select this. Here we go. So we'll take a quick stab at a couple of these and okay, assignment manager, 3.4. Come on. Okay. Preview. All right, let's see. Let's kind of look through here, see what looks good. Mean, variance, standard deviation. Yeah, any of those first three, I would certainly use Excel for any of those. All right, here's an empirical, and there should be a, oh, yeah, Chevy Chev. All right. Oh, I can do this real quick. 6 parts remaining? What in the world? Oh, I think I know what this one's doing. Okay, yeah, this is, okay, yeah, we can take a look at this one. Yeah, this one's actually asking you to count how many of them fit in the interval like I was talking about with that one example I did with the 200 numbers. But notice, excuse me, fortunately this one does not have 200 numbers, so it won't be that hard to do. So this will be a good one to look at. Oh, let me get, okay. I think it probably will, did it change the numbers or not? Let me look and see. Hopefully it didn't. 17, 4, 4, 8, 15. Sometime today would be nice. Yeah, let me try it again. All right, open up this time. I don't know what's going on here. Oh, finally. Now, we don't need to sort these or anything right now. But we will when you do that one part or whatever. But anyway, right now we can just go, what's it asking for? The mean. Now, because the mean is calculated the exact same way, whether it's, all right, which one am I doing? I'm doing this one. There's 2 data sets open. Are they the same data set? I guess I do that a lot. I get frustrated and I start clicking open too many times. We're gonna make sure it matches the problem we're doing. All right, well, I think it's the one on the right. No, it's not the one on the right. I'll take the 17,448. Well, anyway, the mean's done the same way. You can use that same average command. So that's what I say, because there's no difference here. So the mean, whether it's called population or sample, as far as calculation goes, I can just put average. And then was it A1 to A20? All right, there's that one. I'll go ahead and do the variance and the standard deviation. So the difference here is dot P instead of dot S. So it's equal var, I'll do var first, var dot P A1 to A20. I don't know what answer it's going to ask, what order it's going to ask it in the my math lab problem, but I'll just remember, ooh, big old number. And then equals, so I'll just have to pay careful. You might want to do it, one at a time per question instead of what I'm doing here, but whatever you want to do. I'll be able to remember which one is which here. So, all right, there they are. So 10171. Okay, it did do variance first there. That's that big number. 12712523. Grief. 1271 12712523. Yay! All right. Standard deviation. Nearest integer. Okay, I want to check, you know, if it wanted any of the decimals or not. This one had decimals in it. It is not nearest integer, so we'll round that down to 3565. Look at us go. All right, yeah, so plus and minus 1, plus and minus 2, plus and minus 3. Now, let me go back to the data. I'm gonna have to sort it, which is not a problem. Data, sort. There we go. So I'm going to take somewhere over here. I'll just do it off to the side. The mean, I guess I could just use 3565. That's fine. But I'm going to take the mean and subtract one standard deviation. Then we got to do it for 1, 2, and 3. It's 10171 minus 3565. And then I can just copy this, couldn't I, and then change it to plus. I'm not referencing any cells or anything. Now I'll just change this cell to plus. And, oh, crap. All right. So it's 6606 to 13736. I'm going to use so I'm going to kind of fill in a cell. Oh, I don't want to fill in that cell, but I'll fill in the, anyway, it's the first time it goes a 666 or 6606 or higher. There's a better color than that. There we go. That one. And then I don't want to go above 13756. And that would be right here. And then count how many are between there. It's 12. It's 13. Excuse me, it's 13. So then the percentage, just take 13, you know, I'll do it in my head, but you shouldn't do it in your head. But 13 divided by 20, that's 65%. I'm lucky that I can do these in my head because it's dividing by 20. So that makes it easy. Yeah, so you count how many of them are in there, divide. I believe that's what it was asking. Yeah, well then plus and minus 1 standard deviation is 65%. Look at us go. 2 standard deviations. Okay, well, that's all right. Come back over here. And what do? We'll take that same mean equals 10171 minus 2 times the standard deviation of 3565. Now let's see if I can do this correctly this time. Copy, paste it here, and then I'm going to edit the cell and just change that to a plus. So now it's 3041 to 1730. I'll use a different highlight color here. So right there. And then 173, okay, right here. Then the next one, the bottom one will be too high. So you look between those, whatever that beige color is, and you see instead of counting how many, it's probably easier to count how many are not in there. And there's only 2 of them not in there, one at the top and one at the bottom. That's 18 out of 20. So you take 18 divided by 20. That's going to be 90%. And look at us go. 3 standard deviations, probably going to be all of them. I'll just change this one to 3 instead of retyping it. Made that one negative. Okay, I don't need to highlight. I'm not going to do the highlight thing because every number is between those two. So it's 100%. So I like, yeah, that one example I showed you in the notes, that was too many numbers, but I like this one, you know, for a small scale example of doing this. I like it. Big fan. Because that way you're not just torturing. Oh, here we go. Compare. Oh, I don't know. I'm going to say, okay, 65 versus 68%, 90 versus 95, and then 100 versus 99.7. I'm going to say that they're close to the empirical rule. I think it's all right. I mean, I like it. I mean, they're all right. Okay. Because like I said, the $1 million question is how off is off, you know, for it to be considered, because that's kind of a loose definition, but yeah, but obviously I could have, you know, we could have seen if they were like way off, it would have been really obvious, but empirical rule. Heck, I can do this one real quick. And okay, so you see 71, here's the interval 66 to 76, standard deviation is 5. All you got to do is either subtract or add 5 one time to get to these ends. And the empirical rule, when it's plus and minus 1, 68. All right, we're moving right on here. What's Chevy Chev? Let's see, same kind of. So this one, K equals 2. I won't go back to the notes there. Like I said, I don't expect you to know this off the top of your head. You just learned it, but I trust you can find it. So you just go back in the notes. The rule for 2 is at least 75%. Yeah, you're just going to go back and look. So if I take 72 minus 2 times 5, that's 72 minus 10. I believe that would be 62. And then 72 plus 10, I believe would be 82. What do you think? I don't think we need to calculate. Well, I mean, just because I'm doing it without one doesn't mean like you have to be a hero or anything. Not that I'm being a hero. Because I've been known to bonehead this up when I try to do stuff in my head sometimes. But beautiful. So we're going to X out of that. We're done. Move on to the next section, which is covariance and coefficient of correlation. Covariance, we're not going to get super deep into this. All you got to know for this covariance is actually part of this coefficient of correlation. But this is just a matter of Excel. These won't even be on the test, but they could be in an Excel assignment, or I think they're in the homework, you know, but I'm not going to ask these on the exam. So, but they're not hard, but I don't put these on there. So, okay, I could go into a big old explanation of what's going on here, but we don't really need to. But we're looking at relationship between, we're going to talk about 2 values of data, comparing X, Y, just like you would think in the traditional sense of X and Y in the XY coordinate system. I probably should have done scatter plots before I did this. But anyway, you're going to see how this ties in here in the next section. So I probably should have done that first, but oh well, never mind. You'll see here when we do this. Covariance. There's the command. I believe this is always going to be covariance.s. It's not going to be a .p. Array 1 could be, you know, wherever. There's 2 arrays here, one for X's and one for Y's. The order doesn't matter. So let's say, for example, and we're going to do one here in a minute, but obviously when I get to the homework, we'll do one. So let's say if your x's were in A1 through A20, you'd put A1 colon A20. And let's say the y's were in B1 through B20, you'd put B1 colon B20. Yeah, okay, yeah, I should have done 2, 5. Well, you know what? I'll tell you what, it won't, because 2, 5 is not going to happen. Let me just squeeze 2, 5 in there right now. I'm sorry about that, but I'll leave this up here. 2, 5, I can, because I'm going to knock 2, 5 out in just a couple of minutes. It won't take long, but it'll help make this have a lot more sense to it, I think. All right. Sorry about that. I don't think it's going to throw you off too bad. You're going to be all right. Now we're looking at two numerical values, more commonly how x and y sort of relate to each other, which that'll be coming up here in a minute too. But so you see like x, y. Now a scatter plot is because your data is actually going to be paired data between x and y, like once again like x, y coordinates. So imagine if you were plotting x, y coordinates on a graph. So the scatter plot just means if you put a dot, everywhere, you have a value, then it leads to what's called a scatter plot. Is just the collection of all those dots that you plotted. All right. So once again, your x-axis is your horizontal, your y-axis is your vertical. So here's just some examples. Suppose your dots look like this. We would call this a positive linear correlation. What that means is the dots are forming kind of a shape of a line. Not a perfect line. We'll talk about that. They're not exactly in line, but kind of a linear shape. And positive, not in the sense of what you think positive and negative numbers. It's slope, positive slope, meaning that a positive linear correlation means the dots kind of cluster into a line shape. But what it means is whatever the data is representing, as x goes up, y goes up, which represents slope positive. Now, negative linear correlation means the dots form a line, but once again, the negative, that's for slope, meaning as x goes up, whatever y is going down. Like here's some example. Let's say if you're collecting data where for like individual students, and let x be the number of hours studied for a test, and y is the grade on the test. Now you're not going to, I say everybody's different. You're going to get different results. So one person that studies 10 hours might make a 95. The other person that studies 10 hours might make an 88. So obviously you're going to get a wide result. But anyway, that's one that you would expect. As x goes up, you would expect y to kind of go up. And let's see, what's an example of this one? If I use the same test example. Maybe x could be the number of hours, I don't know, playing video games and not studying, assuming that the test is not on video games. So whatever, let's say as that went up, you might expect y to go down, because you're not committing that to study hours, non-productive hours. Okay, anyway. Okay, dots all over the place, no real correlation. Now we're not studying, nonlinear is a completely separate branch of, deeper into, we're not studying that at all, but nonlinear just means the dots cluster, but they form a curve instead of a line, like a little parabola, and so that's okay, but that's not a big deal. We don't have to worry about that. But see, they kind of cluster together, but they're not a straight line. And here's one where I just did an example in Excel of, I just made these up here, made up some hours studied, grade on the exam. And so like on this graph, we're 16, 100 was going to be on there, which obviously is that dot right there. I'm not going to go through and identify every dot, but that's that dot right there, and so each one of those translates to a dot here. And you see they form a pretty good line. We'll talk more about this line here and tonight, actually. probably after break. But anyway, you see that's a good positive linear correlation for that data. So that's what a scatter plot is. So it's all those little coordinates plotted up there, nice shiny little dots there. Time series plot. Let's talk about this while we're here. That's a pretty easy one. That doesn't directly relate to what we're about to go back to, but it is an important type of plot. A time series plot means that really kind of whatever's like on the x-axis, the bottom axis, is some unit of time. This case, for this particular example on the left, it's monthly. But it could be daily, it could be yearly, it could be whatever, but the x is going to be a measure of time, I mean, some unit of time, and then the numerical value that goes with that time. So whatever in monthly sales in January, you can see we're somewhere between 30 and 35,000. So that's what a time series plot is. So I'm sure you've probably seen these kind of plots before. So it's kind of good to know what that represents. So that's it. That's it for 2.5. There's not even any specific homework assigned for 2.5. So, however, though, the scatter plot's going to be part of another homework. So that will come up in the chapter 12 homework, which actually the chapter 12 we're doing today. I know sounds weird, but it's not. It doesn't have to be done. Well, okay, I'm not going to bore you with a bunch of useless information, but we can actually do it now because there's a couple things we're not doing in there. They don't want us to have to cover. So anyway, back to this business. Coefficient of correlation. Now, just we talked about that positive and negative linear relationship with those dots. So now this will help make a little more sense of that, I think. There's a numerical value. Unfortunately, Excel is going to calculate it for us. But years ago, we did this using a formula. It's just a little tedious. It's not hard per se, but it's a sort of a tedious calculation. We used to do it, but now there's no point in doing it now. Anyway, it's a value that's going to range between -1 and +1. That's kind of a weird thing of values, isn't it? -1 to 1. -1 is a perfect negative correlation, and +1 is a perfect positive correlation, meaning -1 means, which is obviously rare that you would have either one of those values. -1 means your scatter plot, your dots, are in a perfect straight line. I mean, perfect. They're just heading downward with a negative slope. And therefore, +1 means the dots are in a perfect straight line. Just, the slope, it could be a different, slope. Doesn't have to be the same straight line, but it would be heading in a perfect straight line upward and positive slope. But yeah, so it's telling you they would be connected with a straight line. That's obviously rare. Here's another Greek letter, rho. We're not going to use this. The numerical value that we use for this is actually lowercase r. Rho is the population value. We're going to be using the sample value r. I should have mentioned r in here somewhere. Well, I got r coming up here, so sure. So here's an example of a perfect negative, perfect positive. But anyway, like on the perfect positive, you could have had the dots could have been like, they don't have to be that slant. That slope doesn't be the same. Let's say the dots were in a straight line, like that. That still would be a perfect positive correlation, but different shape. It just means they're in a straight line going with a some sort of positive slope is all I'm getting at. And 0, yeah. So actually in this idea, when you talk about the strength of a correlation, 0 is the worst one you can have. That's the weakest correlation. That scatter plot I had from the last section where I said there was no correlation, doesn't mean that one was 0, but that one would have been extremely weak. The closer to 0 you get. So in other words, we have like this question. like what this statement here. I'm not going to put this on a test or anything, but I like this statement. All right, where's my? I lost my. Okay. Yeah, this statement right here. Correlation does not necessarily prove that there's causation. You know, some it would, but for example, sometimes you can get relationships, you know, maybe between numbers, pairs of data that really, just because they happen to have a numerical relationship, it doesn't really mean that there's an actual relationship between them. Like, for example, the hours studied and the grade on the test, you know, that makes sense that there would be a relationship there. But suppose that we had data that showed an individual's, I don't know, height in inches or shoe size versus, you know, of course I know it's different with men's and women's, so I guess let's keep them separate. You know, women's shoe sizes, women's test scores, men's shoe size and men's test score, whatever. But the data happened to show that there was a strong correlation. I think common sense is going to tell you, no matter what that data looks like, that there's no possible chance that shoe size could have an effect on your test score. I mean, that just doesn't make sense, does it? So that's what this is talking about, you know, that just because they have a correlation doesn't really mean, you know, shoe size would actually be causing an effect on exam scores. So that's what that's saying right there. So sometimes you can get some weird relationships in data like that.
I give an example. Like I heard about like full moon and crime or something like that.
Okay. Well, yeah, a full moon and crime. Okay. That's interesting. Of course, that would be hard, how you would kind of numerically quantify the full moon, though, because you'd need to have, unless you just came up with different numbers that represent the different stages of the moon or something or another. You know, if you gave them numerical values, you know, that's what you'd have to do that if they were the X, and the Y would be the amount of crime. And I mean, I don't know, unless you just sort of believe in some sort of actual lunar effect or something. I don't know, but yeah, it does seem kind of odd, doesn't it? But I can't imagine. But I mean, yeah. So in other words, there's probably a correlation there that pans out. But can you really say there's a causation on that, though? That's a good example, though. That is. People joke, you know, full moon, does that make you go crazy or something? I don't ever think about what the phase of the moon is, so I don't know if it has any effect on me or not. I don't know. Does the full moon make us do crazy things? I don't know. I guess maybe if there are werewolves out there or something, that, you know, maybe that's true, or I don't know, but never seen one. But yeah, okay, here's where it says R is the sample correlation coefficient that we're using. But that was an interesting point about the moon, and yeah, I like that. So, you know, as I was saying, the closer to zero, weakness. So you look at this, and now why do I have this? I must have keep forgetting to edit this every semester. No harm done. For some reason, I have the same information copied twice here or whatever. Okay, no harm. I'm not going to worry about fixing it now. Of course, I'll probably never remember to fix it, so this will probably happen every semester, but no harm. So that's the same statement that's right up here. So out of these two numbers, which one is the stronger correlation? It's not saying negative or positive, just which one's stronger. So you don't look at it saying, hey, 0.4 is a positive number, so it's stronger correlation. Actually, it's whichever's closest to the edge, with edge being -1 and +1. Now, another way you can look at it is if you just take the absolute value of those two numbers. The absolute value of -0.8 would be +0.8. So that's why it's the stronger one. So in other words, another way to look at this is that -0.8 is closer to -1 than 0.4 is to +1. That's why it's stronger. So it's like zero's the weakest, and it gets stronger going two separate directions, you know, so it's not a strength by one direction, it's a strength by two directions. So, all right, we're getting close to break time here in a minute. So, oh, okay, we don't need all this. Like I said, we used to do, like I said, back in the olden days, we used to crank this out. Just very tedious, but not anything you couldn't do. Here's the correlation coefficient command, CORREL. I'll usually put my X's first and my Y's second. Here's some more, and we're going to use this command here in a minute. What's that? There's some, okay, so it's showing you some scatter plots. That one's saying it's negative 0.9, and that one's saying it's negative 0.6. So you see that the negative 0.9 is a little bit more of an obviously tighter line. You know, obviously it's not. I was surprised actually that said it's negative 0.9. It doesn't look that strong to me, but that's okay. Not going to argue with it. But my point is, it definitely clusters better into a line than the negative 0.6 one here does, doesn't it? It definitely forms more of a linear shape. The same thing. And look at this one, negative point. There's a positive 0.3. See the negative 0.3 and the positive 0.3. Yeah, the negative 0.3's got sort of a downward tilt, and then the positive 0.3's got sort of an upward tilt, but not very good. Not a very good correlation. Hard to really get much of a linear relationship. Now here's a positive 0.6. That's getting a little bit better, and then there's a positive 0.9, which obviously it's getting better. Getting better means forming more of a linear shape. Now, so this, you know, you don't see it here, obviously, but I'll show you this in a minute. So I took that same data and I used the Excel covariance calculation and then used the correlation coefficient calculation to come up with those two values. But you're going to see that in action here in just a second. So I thought I had it written out here. I guess I did. There's the formulas. Well, we're right on the cusp of a break here, but maybe since it won't take that long, I think I could go ahead and just jump into the homework so you can see this. This one won't require, I think, that many examples to do. I think I just do one and that'll be good. And I think sufficient. Not efficient, sufficient. And then we'll go on break here in a second. That will kind of close this out. I think once you just see this done one time, easy peasy, you're good. No, I don't know which one do I want to do here. I'll just kind of jump through here and see what looks exciting. Okay, this one's got a lot of parts. It's not hard, but it's got a lot of parts because it's telling you to compare different ones. Like here's a first weekend and national, first weekend and worldwide, national and worldwide. So it's just a bunch of comparisons, just repeating the process. I don't necessarily need to do that. Let me just kind of pick one where I just sort of do the, let's see. I'm just looking for one that doesn't have a lot of parts to it for right now. This would probably be okay right here. Click on over here. When it does that, so you go over there and click on here. Excel. Now we don't have to worry so much about the X and Y later here. We'll talk more about that after break. It doesn't really matter which one's which at this point, but it does in something that we're about to do coming up. Now it does not. Yeah, we'll just do this one, then we'll go on break. Come on, pop on up for me here. There we go. Beautiful. All right. So you see we got two columns of data. That's what we need. I have an array 1 and array 2. So it wants covariance. Okay. I'm just looking for the command. I think it's just covariance.s, I believe. Yeah, there it is. Look at the dot S. So array 1, array 2, doesn't matter what order you do it in, but obviously I'll just do it left to right. That seems natural. So the command for covariance will be just covariance.s. Easy peasy. I like easy peasy. That's good. I'll widen the column here. Doesn't really matter where I put it, right? Any empty cell there. Equals covariance. Yeah, we're not doing it for P. We're only doing it for S. Well, it wouldn't let me select it there. S. And then what are my, it's not an A1 because the header is there, A2, and it's all the way down to A20, what? A25. So we do A2, A20, it's the first time we've had this with two different things, A25, so but then we put comma separates it, and we put B2 colon B25. So they're both in the same command. They're not, you don't do it for one array, then the other array, they go right there together. That's okay, it can be negative, positive, whatever. Now let's just see how they want the answer, you know, we gotta see what they want as far as decimals or, okay, nearest integer, just wants whole number, okay. We can comply with that. So negative 7483.8, I'm going to say negative 7484. Let's try that. Negative 7484. Look at us go. We are too cool. R is the coefficient of correlation or correlation coefficient. Now I can do two. Actually, if I don't want to say this number for anything, I could just go right back up here. See what I'm doing there? I can back out the command, just do the CORREL, you know. But if you didn't want to get rid of that number, you could retype it. So look at that. See, all I did now is just type right over what I had. So that number is always going to be between -1 and 1. Yeah, this is really a weak correlation here. Now this one's obviously going to want decimal places in it. I just don't know how many. Three decimal places. So let's go back and see what it wants. And what it was going to be. We know it wants 3. So I'm going to go negative 0.145. I don't think I have to put the 0 in front of it, but I will. Yeah, that's a weak negative correlation there. Fantastic. Okay. Let's look at this. Well, because it's closer to 0 and not closer to -1, you know, like that'd have been like negative 0.945, the answer would have been strong negative. Well, you can take strong out of the equation and you can take positive out of the equation because the number is negative. I mean, I guess they're not using weak negative as a choice. You know, I would have picked weak negative if that was a choice. So the only logical answer left has to be that one because the other ones are just completely wrong. I mean, weak is good, but positive is not good. It's weak negative. Excellent. Look at us. We're too cool here. All right, that worked out. I'm glad we did that. So that's all that's involved in that section. Yeah, we may end up doing really well here. Knocking these things out. Now I think we need break time here. 10 minutes. That's what we seem to usually do, right? 10 minutes. So
Are you going to go over 12 tonight?
Am I going to go to 12 a.m. tonight? What?
So if you're going to go over all the chapters.
Yeah. I mean, actually, we still won't take the whole entire time to do that. So yes, we are finishing everything tonight. And then at the end, we'll discuss, you know, obviously I'll put an announcement on Blackboard, but we can, if you want to have input regarding the, you know, the dates of the exam, that'll give you a chance to have input. You know, if you don't, that's fine too. But Ultimately, it'll be my decision, but I'll listen to what we say here, and then obviously I'll put that in Blackboard. But yeah, we're not going into anything new beyond this unit. We're absolutely finishing this tonight, no question. So yeah, that's a good question. So all right, well, so I'll see you in about 10 minutes or so. I'll just kind of start talking and whatever. Let's see. Okay. All right. I'll stop share for a minute. All righty, welcome back. Let's get the share screen back up. I just got rid of it so I paused the video. Sometimes I forget to do that. I didn't have to, but it just makes it easier when I'm processing the video. I don't have to worry about cutting that part out. Wish I could remember to do it every time. But then I got to pause and make sure it's back on. But now I see it says recording, so. Yeah, I just edit out the video part. So let's just share a screen for everybody here again. So yeah, we're doing great here. I'm double check. I think there's only just the stuff from 12 is the only thing that's left here, I believe. Because I knocked out the 2-5. We've done 3-4 and 3-5. Just did a homework problem on 3-5. And only the last thing will be the 12. And that'll be it. Okay. So let the games begin. Like I said, we're going to end up finishing a little, definitely ahead of time here. Maybe I'll have to do an extra homework problem or something and go back and kill some time here, but that's all right. Regression analysis. Now we're just scratching the surface of this topic, just kind of doing very little of it here. But yeah, I remember a long time ago in grad school, you took a whole class on that. You can really learn a lot of stuff, and we're just doing simple, basic, knowing what regression analysis. That's good. So we're using it's using the XY data. And then we're trying to, from that information, we're trying to see, depends on how well the data is related, how well it correlates with each other, can we use the value for X to predict Y? In other words, based on a bunch of X's and Y's we observe, could we then come up with an equation to help try to predict Y based on some sort of X? That's the idea. The Y is the dependent or response variable. And then the X is the independent or predictor variables. Now this says one or more. Now we're not covering that. That's one of the things in regression. There's also called multiple regression, where you can try to use several factors to predict the response variable. You could have several X's. Now, I know that kind of defeats the idea of how an equation graphically, that wouldn't make much sense. So those aren't usually done graphically, but you could have like a X1, X2, X3, and X4, and whatever. If you're trying to predict something, then you could take variables in and out of it. You take one out and look at your results and see if that looks better. And that's a whole big old thing, it can be a whole in depth, but we're not getting that in depth. So we're trying to build what's called it's also called a regression equation, prediction equation, least squares line of best fit. It's got a lot of names that are all kind of mean the same thing. Now you don't have to worry so much about this equation right here. We're not going to do much with this. those are actually those are betas, Greek letter beta, beta 0, beta 1. That's actually a Greek letter, epsilon. Now we're going to worry about just the standard equation down here. It's basically, this is just going to end up being y equals mx plus b. But anyway, I'll just mention that this error term is there because anytime you're using sample data to predict population, there's always some sort of built-in error there or something. So that's not your, when I say error, not errors and a mistake, it's just error in the process itself. That not like means we made a mistake, but in other words, saying, you're not likely to be able to predict the population results with 100% certainty. So anyway, so you don't have to worry too much about the theoretical here. But it's essentially, okay, let's see. So we have a slope and a y-intercept, which I'll come down here and show you. The slope, the B1, that's beta, but we're going to call it B1 when we come down here. That's the change we expect in y per unit x. Remember slope from algebra, rise over run? Same idea. In this case, we're saying the run is always 1, so if the slope was 3, that would be the same thing as saying 3 over 1. So for every 1 unit x increased, y would increase by 3. And so in other words, if the slope was negative 2.5, every 1 unit increase in x. So that's always the same. We're always assuming 1 unit increase in x. We would then say that would be decrease of 2 units in y if the slope was negative 2. So we would not have slopes like we might have had back in algebra, like they need to be single number values. So they need to be represented as if they were over 1. So we're not interested, like, back in algebra, you might have been asked to calculate a slope and, you got 3 over 2, like that. That's okay theoretically, but we need that to be 1.5 for what we're doing. We need to make that, in other words, a single number. So that's then saying if the slope was 1.5, yes, this is telling you for every 2 increase in x, y would go up by 3. But we always want the bottom to be 1. So that's saying for every 1 unit increase in x, y goes up by 1.5. We don't care that they're whole numbers or not. We want basically a single number where that's an implied 1 on the bottom, because obviously 1.5 is the same thing as 1.5 over 1. All right, so it needs to be represented in that form. Now it's written a little bit different than what you might be used to. We're used to seeing y equals mx plus b. But the way this is written is they put the y-intercept first. B0 is the y-intercept. It would be the same thing as your b in the y equals mx plus b equation. And then your B1 is the same thing as M. And this little y with that little caret, we call that y hat. That's okay if you don't know that, but it's got a little, the caret's considered a little hat on top of it there. So we call that's the predicted value. So what this all boils down to is, like I said, we're going to be using technology to do this, but if you take a bunch of data, a bunch of paired data, and then, you come up with this line of best fit, regression line, whatever, it's all the same thing. And then you come up with that, then you could just start to predict a value for y. You could just plug in just some random number you wanted to predict for x and calculate it, and that's what you're predicting y is going to be. That doesn't mean y is going to be that value. You're just estimating that's what you think it's going to be based on the other measured data. That's, a lot of educated guessing in statistics. It's really, so it's kind of written backwards there. So we just have to get used to that a little bit. And other than that, we'll be okay. And let's see what we got down here. Here's an example I copied out of here. So here's an equation. They are, what are they telling us this model represents? The model represents we're trying to use X to predict Y, where X represents the number of classes missed during a semester. Can that be sort of used to predict the final exam score? That's what they're trying to make. You know, you would think theoretically the number of increased absences might affect the final score. Although in this day and age, maybe not as much. It depends on, you know, if you're an instructor or somebody like me that has a lot of stuff posted, you know, and all kinds of stuff, and then these recorded videos, you know, absences might not be as big a deal. But back in the olden days, you know, when I was kind of in school and you didn't have all this kind of stuff, you know, if you missed a lot of class, it was kind of made things a lot tougher. And getting somebody else's notes wasn't always helpful because it's kind of sometimes hard to interpret someone else's stuff, you know, or whatever. But that's it's probably harder to do unless they're teaching a class to where there's in-class activities or something that are part of the grade. You know, obviously that would make a difference. But anyway, so here is 85 minus 5 times X. So the y-intercept here is 85. So that's basically meaning the y-intercept always means X equals 0. So that means they're predicting that it's going to be an 85 if they have the average person should make an 85 if they have 0 absences for the semester. The predicted mean final score for all people would be 85. Doesn't necessarily mean one individual. You're kind of predicting an average, but you can also be predicting an individual at the same time too, you know, so. The slope. Now let's look at the slope and what that means. Slope is -5. Okay, so we got negative slopes, we got a decrease. So that means for every 1 unit increase in X, we expect a decrease of 5 units. So when you say decrease, that implies negative, in other words. So you don't say decrease of -5, you just say decrease 5 units. So one absence. Now in the context of this example, absences are X. So we are predicting that, of course they're saying the predicted change, which is right. The predicted change is -5. If I word it as decrease, that just means 5, you know, same thing. So they are predicting for each absence, you're predicting the final exam score to decrease by 5 points per each absence. Wow, that seems like a lot, but oh well, we'll just go with it here, whatever. I won't overanalyze this. But that's what it means. And for every 1 absence, we predict the change in the final score to go down 5 points per absence. Okay. All right. So, you know, that's something good to know because I could certainly ask that on an exam. I like to sometimes, I like to ask the meaning of the slope, you know, interpret it in the context of a problem like this. And that was an excellent example right there that we just saw. That's why I just kind of copied these out of the book because I liked them. Now, this is super duper duper easy here. You'll love this one. Now, suppose that we already have this equation. Like I said, we're going to use technology here in a minute, show how to get this equation. But on a test, homework, you're going to have to come up with the equation. On a test, I'll give this to you. And then it's asking you, all right, now we got to read this carefully though. I try not to make this too tricky here. Yeah, they need to clarify that this is kind of everything's in millions here. Everything's in millions. So, yeah, I don't know. I try to make sure I clarify that because the idea is easy. Whatever the X is, you plug it in, then you predict your Y, but they should say somewhere here that everything is in millions. Did I zoom in too far? Or maybe it says it over here to the left. I just don't see it. No? Yeah, that needs to be clarified because so they're plugging in 4, but that 4 represents 4 million. But that means everything's in millions here. You have to have, everything has to be the same unit of measure here. It's not going to work too well. Let's see. Okay. So for 4 million customers with X being 4, you plug that in there and you see in the equation, you get 7.0879. So that's an easy calculation, but that answer automatically is in millions. I don't know. That's not bad that we looked at. I think it's good that we looked at this, but I kind of prefer just plugging the number in directly, but I can see why they would do it, using this in this format where it's not already in millions instead of using gigantic numbers here in these equations. Just convert everything to millions by dividing by a million. But anyway, the idea is just a matter of plugging in the X and getting the Y. So it's really, other than this tricky unit thing, the idea is really pretty easy. Okay, so let's take a look at this example. Let me zoom out. Here's another. Okay, so it's giving you the equation. Now, I'm not telling you what X and Y represent here. I didn't, not that it was a big secret, just I didn't really define it as anything. But anyway, here we have a positive slope of 3.42. So whatever X and Y are, that means for every 1 unit increase in X, we're expecting Y, or the average for Y, to go up by 3.42, whatever that's representing in this case. Now then here, predict the value when X equals 10. So you just plug 10 right in there. So nothing tricky on the units here. That's why I just, no millions or anything. So you just plug 10 in there and you get 86.76. Now, this might have been good data for that one where I had, number of hours studied on a test. That matches up pretty well with this. So in the sense that, that would be reasonable. Now, one thing to consider, like when you, especially, when you're predicting values here, you don't have to worry about this per se. I would make sure I gave you one in the range, but your predicted value needs to be something that is within the range, kind of the range of your data. Because let's say, you had your equation. Let's say, hey, if I studied 40 hours, I'll make 138 on the test. So that's the problem you run into, is that you'll come up with values that don't make sense. In other words, they wouldn't be, you're not going to make 138% on the test. So there are a limit, but that's not something you have to worry about. I'm just kind of mentioning that in general or whatever. So these predicted values need to be somewhere in line with whatever the data is representing, so it doesn't come up with ridiculously stupid answers there, so. Okay, 120 plus 5x, weight Y in pounds, X is in inches. So this positive 5 means for every 1 inch in height on average, like I say on average, obviously we're all different, so, but they expect on average, the person should increase by 5 pounds because it's a positive 5 slope. So there it is, increased by 5 pounds. So the answer would have been, if negative would have been, well, 5's not there, so it's wrong anyway. But anyway, the word decrease would have been the answer if that would have been a negative slope. It would have had decrease in there. But obviously this one is. Here's another one where you just predict the value. So you just plug in. I don't need to do that one. I think you can do that. If you have any questions, just send me a message. Plug in 63 for X right here, and you'll get rounded to 76.0. Easy peasy. That's a good question. Now, for Excel purposes, not exam purposes, for Excel purposes, you will use these commands to come up with the answers, to come up with these equations. But for exam purposes, I would ask you something like these two questions right here. What does the slope tell you? And then what does, or I could even ask what the y-intercept tells you. Maybe, but more likely the slope, and then predicting a value. So that's as far as that goes. But the homework, though, we gotta come up with these. So you come up with these separately. The slope will be your B1, and then intercepts your B0. And you got to be careful when you're plugging them into the equation. And you also got to be careful here, too, when you enter these. So we got to read the problem carefully, make sure we can identify correctly what are the X's and what are the Y's. If they just flat out tell us what X and Y are, that's great. But if they don't, as long as they make it clear what is being used to predict something else. In other words, whatever we're using to predict is the X, and whatever is being predicted is the Y. So we'll see how that comes up. Now if it just says X and Y, that'll be easy. But it may be a little bit different. But it's got to be at least clear enough or whatever. Like this one would have been obvious that we were using our study to predict the grade on the exam. So that would be easy to know that this was X and this was Y. But notice, though, in the commands, notice what goes on in the commands. The Y's go first and the X's go second. Whenever we did covariance and correlation coefficient earlier, that did not matter. You just put one of the arrays in, you put the other arrays in, the order did not matter. But for here, it absolutely matters that the Y's go first and the X's go second. So we do have to be extra super duper careful here on this, which you're going to see me do in the homework here in a minute. Now, we don't need this data analysis thing here to do this because that was just another way that produces this or whatever. But I can show you that, but we don't need that because you can just get them from. If you want to look at that, we can. But this is this works here. So, but anyway. So what I would have done to get this slope right here, like I said, you're going to see a homework problem here shortly. So is the Y's are what? B3 to B17. So to get the slope, I would have put the Y's first. B3 to B17, comma, A3 to A17. That gets my slope. The intercept, I'm surprised I didn't write the equation out here. Why didn't I write the equation? Maybe I didn't. That's weird. I'll write it down there. I should have had that included just so people can see the result here. My bad. I'll have to maybe save this and then repost it. But anyway, so you can just see it in the context of an answer. And then the intercepts for the y-intercept, you just use the command intercept, the y's first, and then the x's. So to get your regression line equation, yeah, that is not in there, is it? Let me get rid of this blank page here. So then if it said do this, and then what would be the equation? The equation would be, doesn't matter how many decimal places I use. I'll probably kind of round it down a bit just to make proper space here, but be y hat, and we'll put the intercept goes first. Like I showed you earlier, that's just the way it's done for this or whatever. It's not done in the exact mx plus b order that we learned in algebra. Actually, it's then b plus mx, which mathematically is the same. So the intercept goes first. I'll just use two decimals, 49.29 plus 3.33 rounded x. Okay, so that would be then, so you get the slope and intercept commands, and then to get the actual equation that goes with it, there it is right there. So in case it asks us those, so you know the intercept's the first number that's by itself, and then the y-intercept, and then the y-intercept's the value that goes first, and then the slope's the one that's always attached to the x. Yeah, I'll show you this data analysis thing one time, and I'm not going to redo it for these numbers, but I can easily take a homework problem and do it both ways. You know, I can do it just by putting in those commands, or I can do it this way. And I guess that just gives you choice on how you want to handle it. Totally up to you. Anyway, all right. I was like, is that, yeah, that was it. Because this used to be at the end of the course, and we used a little more information that we would have learned later to do this, but I don't know. It got moved up, which that's okay. We're just not able to do some other things we could have done. That's what they want to do. I just work here. I go along with the flow, whatever they tell me. But there's some other stuff in here that we would have used, but we can't use it now because we need later information. All right, well, we can go right to the homework here. So we're doing pretty well here. So so that we take a little more time on this, I guess. All right, well, let's just see. We got 4 problems in here. Yeah, here comes that scatter plot idea here now. But we're going to do this in Excel, but it can be a little tricky. You just got to kind of, you know, we're going to do it together here, you know, to look and see which, because it all depends on how it scales it. You know, you got to look at it, but we're going to use the technology here. So we're going to see. Okay, this one involves wine here, so an alcohol content. So sample of wines. Now here's what I was talking about, the wording, you know, it doesn't necessarily say X and Y, but it gives a key statement here, which goes what I said earlier. So you see that right there? Predict wine quality. That guarantees you the wine quality is the Y value. So once again, whatever you are predicting, that's your Y. Whatever you're used to predict it is the X. So the only thing, blah, 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 based on alcohol content. So we're using alcohol content to predict wine quality. Now, some of the homework may mix these up a little bit. What we can look and see, I may not do every one of them, but I've seen some of them where they swap the labels here on the axis, you know, so you got to pay attention to which one's which. This one, they don't. So since all the answer choices are the same, you know, that makes it easy to know that the X has to be the alcohol and the wine has to be the Y. But they could have done this with one of the answer choices, switching them around. So in that case, we could have eliminated anything that does not have alcohol content on the bottom and then wine quality on the y-axis. All right, we're going to get this data. And of course, we're absolutely not going to plot this, plot this data. We're going to work as a team here. But sometimes, you know, the graph, the plot might look a little different because of how it's scaled. I mean, the general shape will be the same, but it involves the X and Y scale that might make it look a little different. But I generally don't have too much of a problem figuring these out, so we'll see. Especially if the answer choices are quite unique here. All righty. Now I'm going to go insert. I think that's the scatter plots. Yeah. Okay. I don't know if I tell it. I can't remember if I put the commands in first or it needs. Oh yeah, it must. I think it needs. Okay. I got to get rid of that. Now, if these were given to you in the wrong kind of order, I guess what you could do is you can copy a column and move it over to the right of it. Let's say these were reversed, because I'm going to assume that when I highlight these, I could probably keep the label in there, but let's see what it does. Sometimes it'll ask you with commands, to tell it there's a label there. This might work. It might, hopefully it'll just show the label. But I'm assuming it's going to interpret that the left column being X and the right column is Y. So that's what I mean about if they came out the wrong way in Excel, you could switch them so that way the scatter plot will interpret it correctly. All right. So now our goal is, well, we can obviously make this bigger, and then you can click on the homeworks and make those bigger too. So we're trying to match the picture that looks like that, so we can zoom in on, I think is it this one? Let me go back and forth here. So we're trying to see what looks like that. So you see what I mean? You got to kind of play around with it a little bit. I think it was that one. Let's look at the ones at the bottom and see if you can kind of match them up. Yeah, they're kind of closer together here because the scaling. I like this one. So if you want to yell at me real quick and say that's not it, please feel free to chime in there. I think it's that one. So like I said, it's a little tricky, but so now you see me do it, you kind of see what you'll be doing there, just trying to look like you're just trying to match it up based on what Excel showed us. Fantastic. Look at us go. All right, got a word type situation here. So it's telling you B0 is 2.4, that's your y-intercept. B1 is your slope of 0.4. Interpret the meaning of the slope. Now they're just using the generic B1 here. They're not even using the values. I'm not sure why they even put the 0.4 there. Oh, actually they are using the 0.4 in a couple of the answers here, but well, anyway, so we have to read this correctly because remember the alcohol content is the X and the quality is the Y. So that means for every 1% increase in alcohol, we're expecting the wine to increase by 0.4. So which of those looks, B is obviously wrong because it has to be expressed. C is wrong because it's saying, well, first of all, these are always going to be an increase. The X will always be increasing by 1, but it's got the word decrease in there. D is just complete nonsense, but B A is correct. It just didn't actually put the number 0.4 there, but if they would have put 0.4 there, so for each increase of alcohol percentage by 1, the quality rating increases by B1, which is 0.4. So A is the only answer that makes sense there. I don't know why they just didn't put the 0.4 in there as part of the answer choices. Okay. Okay, now to predict the value at 11%, we have to come up then with this equation. We have to come up with that y hat equation. And there could be other ways. I'm sure a lot of you might discover there might be a way within this scatter plot, if I remember correctly, but I don't remember correctly. I don't want to waste a lot of your time, that it might be a command where it'll put that, I know it can put that line in there and it might give you the equation with it also or whatever. But I don't want to, I should have looked at that. I could possibly Google that or something where it's always amazing things what this can do. Where I know the line, because you saw that one thing I had with the grades and the hours studied, where I had that regression line in there, but I don't remember how I got it in there. But then also I think I've seen it where it might show the equation for it. Okay, but anyway, never mind. We can, if not, we can just go back to the way I have it done in the notes. So that's something you can, obviously, if you research that and figure that out, want to do it that way, that would be just terrific. But I'm afraid I'm going to get obsessed with this if I'm not careful and start trying to figure this out myself. Knowing me, but I think it's, anyway, but there's no problem. We can just do it with, I'll show you that data analysis command also. I'll show you that way to do it too. But if we're going to use the intercept command and the slope command, it doesn't really matter which one I'll do first. I'll do the intercept first because that number is going to go first in the equation. Intercept. Okay, now, very important. Very, very important that we put the y values first. Very, very important. The y values are in C2 to C13. Oh. C13. Very important. Are you get, and then the x, the x's go second. I know that does not seem logical because it's complete opposite of like rectangular coordinate system, where x goes first and y goes second. You just have to sort of, you don't have to like it, you just have to accept it if you want to get the right answer. I wish I could give a good reason why it was programmed that way, but okay, that's the intercept, and now I'll do the slope. So now the same thing, same order. That's good. So C2, C13, comma, B2, B13. All right, I'm going to copy these over to my Scratch page. I have to use, I wonder if I may need the snipping tool. This might not work. Oh, it did work. Okay. Now, I'm not going to write out, I'm sure that won't affect the answer that much, but I'm not going to write out all those decimal places. So just to show you then how the equation comes out, then I want to use a few of them though, just to, because I don't know what the accuracy requirement is going to be to get this answer right. 4 maybe, I don't know. Yeah. I'll go 2. So I did the intercept first. In the notes there, it shows the slope first. Just pay attention. And then plus, because it's positive, and I'll use 4. I'll go 0.4386. And this is the slope, so that's going to go for the x right there. Hopefully that'll be enough to guarantee that, and then the x. Now, then what we do is it's asking us to predict 11. Now 11%, because the axis is given in percentages, we don't convert that to decimal. We just use the number 11. I think that's right. We'll find out if I'm wrong, but I don't think we have to convert that to 0.11. We should just be able to use 11 because I believe it's already in percentages. So we just put 11 in here. Y hat of 11. 0.49 plus 0.4386 times 11. And you can do that in Excel or just in a regular calculator, whatever you want to do. I'll just do it in a calculator. So I'll go 2.4149 plus 4386 times 11. $7.2395. Now let's see what Excel wants for its decimals. 2 decimals. So I hope we use enough of them there. So that's going to be, I believe, 7.24, if I remember correctly. No, wrong. It's not what I wanted to bring up. So let's, calculator. Golly. 7.24. Let's hope that maintained enough accuracy there by only using 4 decimals. 7.24. Hooray! Okay, so now you see, so you have to get that equation then to be able to get that answer. Now let me show you the data analysis. I mean, that was fine what we did. You don't need to do that, but I promised you I'd show you. So now I think we've talked about the data analysis. That's, well, it's an add-in, so you have to kind of add it in. If you don't, you don't need to do it. You're fine with what I just showed you, those individual commands, but it's different the way you do it on PC versus Apple. But it's easy how to, you can just Google data analysis add-in and you can find simple little YouTube videos. But, if you click on data, if it hasn't, that'll be blank over here to the right if it hasn't been added in. But mine's already been added in, so it's there. So if you click on that and go, I don't see anything, that's the reason you would need to add it in. But the point is, you don't have to add it in. So I'll go ahead and bring it in just to show you. Just learning different ways to do it. And the command for that is regression. This one wants the Y value. So what I'm going to do is watch what I do here. So the Y values are quality. I want to keep that top. If you keep, dang it. I want to keep, I hate when it all goes haywire like that. I need to undo all this, whatever I did there. Undo all that mess. Wait, let's see. Were there 13 of them? Was that right? Or not? Yeah, it was 13, so up to cell. So I guess that's okay. It's not. I hate when Excel does that when I get. I'm going to put the Y's in there. I'm going to choose the label. So you got to do that for both. If you're going to either choose a label for one, you got to choose it for both, or you can ignore the label. So if you keep the label, you just have to then check the labels box. So in other words, if you don't use that first row with the labels and you start at 2, then don't check the labels box. But since I included it, now it knows that the labels, the tops are labels, and not to mess up the calculation. Output range, I don't know. I'll start it out here to the right, P2 or something, where it doesn't overlap the scatter plot. And then it'll just go to wherever it goes to. That should be good enough. I can scroll over here. Usually it doesn't take that long. Why is it not responding? There we go. And there it is. And then, yeah, because when it does that, then it's, notice it tells you down here when you the labels. It doesn't tell you the Y, but it tells you, it shows the X right here, alcohol contents, the X. Well, anyway, so there's our slope and then our y-intercept right there. So they come out right there. So, okay, yeah, I just wanted to show you that since it was in my, mainly because it was in my notes. I figured at least I could show you. But you're probably fine with just doing those commands individually. Let's try another problem while we're having fun here. We're almost done. Oh, we got, okay. What does this say? Yeah, this one's a little tricky because the correlation coefficient really tells us more about the quality than anything else, and it's not asking for that correlation coefficient here, unless they just want us to visually interpret the scatter plot. That's another thing the scatter plot might show with the right commands in Excel. There might show the correlation coefficient, but because that's what's really going to tell how well. But anyway, well, okay. Anyway, let's see. We can eliminate A and C because it's not, alcohol percentage is not affected by the wine quality. It's the other way around. So it's either got to be B or D. Oh, I guess you could just match it up by the slope. Okay. All right. We don't have to worry about that. Yeah. So it's either B or D. And then what was the slope? Was 0.4. Well, oh, you know what? I did. Well, that's okay. I did all that regression stuff for nothing because actually I didn't even realize. I thought it was just giving those as arbitrary numbers, but it gave us those numbers that we calculated. But you see, it's severely rounded. I'm glad it liked my answer, though. I'm surprised it didn't give me any trouble. Yeah, it already gave us the B0 and the B1. I'm sorry. That's okay. We might need to do that in another problem anyway, so it probably didn't hurt to do it. So that was the B0 and the B1. So I don't know why I just thought that those were completely unrelated numbers. So it's either B or D. So and the slope is 0.4, so it's got to be D. Each 1% alcohol will lead to an increase in the wine quality of 0.4. All right, so let me go through here and hopefully we can find one where, so I don't feel quite so foolish again here, where we actually do. Let me look at the completed problems here, and I'll pick what I want to do. What I want to do here. Because maybe there should be one where we actually have to, yeah, okay. All right, thank you. Okay. I wasted your time doing it on the last one, but it won't be a waste of time for this one because you can see part B has it. It probably has it for the rest of them too. Yeah, this could be a good one. Let me just look at the next two problems, see if there's anything weird going on in these. Is this pretty much the same? Let's see. Yeah, that one looks familiar. I guess they should look familiar, but. And starting salary and job thing here, okay. I don't know, this looks interesting. Let's try this one. So yeah, those next three were about the same. So now you learned on the very first one that you don't have to calculate the B0 and B1 because it was actually given to you. At least, so here we'll do it. We have to do it. Okay, MBA, tuition, blah, blah, blah. Okay. So once again, here it's not, some of the times it might tell you specifically, like I said, what X and Y might tell you that. Here it does not, but it gives you the effective wording necessary to identify what X and Y are. Obviously, it would make it a lot easier if they told us, but as long as it makes it clear, I'm happy with that. It makes this clear. I think that one, I might go back to that other one here in a minute. We don't work it out. I think that one with that tear plate gap rating or something on it, I think that one was a little tricky if I remember determining the X and the Y on that one. Maybe not. I don't know why I'm just having flashbacks from last semester. But this one is okay. Tuition as a predictor of starting salary. That means tuition is X, starting salary is Y. And that kind of makes sense because you're looking at it as, you know, or if you're spending a lot more on tuition, is that influencing what the salary might be? But here, that's clearly worded in my mind that indicates that X is tuition and then Y is salary. Okay. Now we're going to have a little help on this one here when we do the data, because look at before I even bring the data up and do the scatter plot, unlike the last one I just did, we have, they mix up the X's and the Y's. Like I told you, that might happen, you know, and sure enough, it's happening on this one. I don't know if the other two, the middle two does or not, but notice this one, B and D cannot be correct because it has starting salary on the x-axis. So right off the bat for this one, right off the bat, it's either A or C. All right. And this will be easy to identify because, you know, one of them is positive correlated, one of them is negative correlated, so it won't even be, you know, once we look at the scatter plot, it'll be super easy to predict. I'm guessing it's going to be A because you're thinking tuition increase. You know, doesn't guarantee it though, but I shouldn't assume it. But I would think it would make the salary would increase. In other words, I would think people that are paying out the wazoo for a Harvard MBA are probably making pretty strong starting salaries. Okay. So this one will be, scatter plot will be easier to decipher, I think. So all righty. So I'm going to highlight all these. So it looks like the scatter plot didn't matter whether that label was there or not. I didn't notice. I guess I could have, it didn't label the axes, but once again, that could be something that you have to select, you know, within the graph itself. I have not worked with these graphs in years, you know, so I'm not quite as fluent on the detailing of them as just, you know, I just do the generic stuff, no problem like this, but the detailing is a skill in of itself there. Oh, there it is. I wonder where it went. Okay. Okay, so, oh yeah. Oh, across the top, it probably did the last time too. So across the top, it shows the Y. It doesn't bother to show the X. It's just showing what's being predicted, not the X. Well, I couldn't get that to move over, but I'll probably get rid of it here in a minute. Okay, so it was the positive slope. So that makes it easy to identify here. Has to be A. So if there would have been another positive slope that had the correct X and Y axis, I would have maybe had to look at the graph a little bit closer, but didn't need to for that one. All right, B0, B1. Back to the All right, I need this to get out of my way. Yeah, okay, I can shrink and ink it here. So I'll tell you what I'll do here. I mean, when you're doing this, you don't need to do it, but I'll do it for your benefit. I'll put intercept here. I'll put slope here. But then I'll do the command right over here, just so that way you'll know which one I did. So you don't need, obviously you don't need to label it as long as you realize what you're doing. So this one, it's equals intercept. Maybe that one with the plate gap and the terror rating, maybe it has the X's and Y's reversed. So something I'm flashing back to being weird about that problem. I may have to go back and look at it. Like I was talking about earlier, if they were reversed, well, this one, you don't have to worry about if they're reversed. You just type them in there. You know, you can put them in there. It's just the scatter plot. They have to be arranged to come out in the right order. Here, as long as you know, even if the Y's were in column 1 here, that would be okay, as long as you knew that they were the Y values. If they're in the first column, that's okay. So here it's then B2 to how far down does it go? B38. B2 colon B38 comma C2 C38 that should be my B. Oh, hey, whoa. Oh, I put in, sorry, A. Not, where am I getting C from? Good grief, I'm glad we're almost done here. A, sorry about that. Like, what in the world is he typing in there? There we go. And so this one, slope, will be then equals slope. B2 to B38. Comma, A2 to A38. See, make sure I didn't at least make the same mistake twice. All right. So let's see what it wants. So the intercept should be 0. The slope's the B1. How many decimals? What does it want here? B0 says nearest integer. B1 is 2 decimal places. Negative, so that's going to be, so I'll go negative 12616, rounded. B1, 2 decimals. That's my slope. 2.41. Look at it. Woo, good job. Interpret the meaning of the slope. All right. Usually it's supposed to be 1 here, but maybe they're using units of 100 here. That's what's confusing me. If this is in hundreds, I guess we just multiply. I guess you just multiply the slope by, we'll just multiply the slope by 100. We'll try that. Round to the nearest dollar. In normal situations, like on your exam, it's going to be a per 1 unit increase, so you would just use the slope. So here they're trying to trick us a little bit. Now we have to know the X's and the Y's, so that's important. So A is wrong, so it's a tuition increase. the mean starting salary increase. So our slope was 2.41, I believe. Oh, it's right there in the problem. What am I doing? Sorry. It's 2.41. So we just take that number and then multiply it by 100 to match it up with that. Okay. In other words, so 1 would have been 2.41, but 100 with them would be 241. Little sneaky, but now you'll know for homework purposes. I won't do that kind of nonsense to you on a test or anything, but predict a salary. Okay, so that we have to, now I'm just going to do this straight in the calculator. So your B0, remember it says the equation is always B0 plus B1x. So if I go on the calculator, I can go negative. Make sure you use that bottom minus sign, not the, because it doesn't like it. You try to use the subtraction on the right as a negative coefficient. It does not like that. 2.41, and I already forgot what the x was, but I'll go back and find it right now. Predict, okay, 54724. Okay, so I'll put 54724. Oh, the calculator. 54724. Probably nearest whole number. Yeah, I'll check though. I won't assume it. 119269. Yeah. 119269. So yeah, you're trying to use that, but it doesn't mean that's exactly what's going to happen, but that's what you're trying to predict. Say, well, we pay this, what do we think it's going to be? Doesn't guarantee anything. All right, last part of this question here. Let's see. What insight? Oh, let's see. I don't like A here. Don't like B. C might be good. Mean starting salaries upon graduation tend to be higher among programs with higher per year tuitions. So this basically saying the higher the per year tuition is higher mean average starting salary. So I think we got C going on here. Hope I'm right. Terrific. All right, so I'm going to stop content-wise. I'm just